Hello everyone. Today we will study one topic from stereochemistry, that is conformations of cyclohexane. So we can see this is the cyclohexane moiety over here, cyclohexane moiety over here. Okay. The cyclohexane is most stable and most common acyclic ring system, and hence the conformational analysis of cyclohexane has been extensively studied. The the structure of cyclohexane is very important, and it becomes essential to understand because this particular moiety found in many uh, pharmaceutical agents as well as natural products. Cyclohexane ring exists in non-planar or puckered conformation to avoid the angle strain. In these conformations, the angle strain is practically absent, and hence they can be called as a strainless rings. So when we talk about the cyclohexane and its derivative, it don't have that planar structure. If you consider benzene, we know benzene, all the atoms are present in one plane. So ultimately that moiety is planar in structure. And if you remove that all three conjugate double bonds, then that remains what will be the left behind, that is the backbone of your cyclohexane. But just removing the double bond will make it non-planar, and all six carbon atoms will not lie in a one plane. So that's why it is said that the ring will exist in non-planar conformations, and then again it will avoid it will again mm, not a single structure, it will acquire different structures, and that are considered as a conformation. We will see that one by one. And then when we talk about the angle strain, so why these rings will acquire particular conformation for a particular structure to avoid the angle strain. So practically the angle strain is absent, and by thereby it will reduce their strain, and when it will reduce its strain, ultimately it becomes more stable, it becomes highly stable. So it should be noted that all these conformations are obtained by particular rotation or the partial rotation about the carbon-carbon bond. So we can see here all the this carbon-carbon sigma bond, the different conformations of these cyclohexane rings are obtained by the partial rotation, because these atoms are held by the ring system. The atoms are part of the ring system. That's why the full rotation is difficult over here. So partial rotation is uh, taken place over there about carbon carbon sigma bond. However, due to this ring system, the molecule will be more rigid, and hence the molecule will have less freedom to assume all the conformations. So each and every conformations to understand, to assume it, that will be very difficult, because it is a cyclic system. So there are certain conformations, out of that one or two are more stable conformation. We will take that example. So if we talk about uh, the conformation of cyclohexane, then the very first one is chair conformation. So chair conformation of that, here dimensional structure, it may be difficult for you to understand that. But see, now all these carbon atoms will not lie in a one plane. The chair like geometry is obtained over here and called as a chair like conformation. So in chair form there are two sets of six bonds. There are six CH bonds. So if you count that, six CH bonds which are parallel to axis of symmetry. So axis of symmetry means ultimately, if you consider center of symmetry, then there will be one axis, and then there are six CH bonds. Means ultimately you can clearly see here carbon hydrogen bond, the hydrogen which are shown in a red color, that will be the six hydrogens which are vertical, shown in which are vertical over here, that carbon hydrogen bonds which are vertical over here, and that will be parallel to the uh, uh, center of symmetry, the axis passing through that, that is axis of symmetry, we can say. So That bonds are called as a axial. In chair conformations, there are two sets of six hydrogen atoms. Means ultimately there are two types of hydrogen actually, the axial and equatorial. And what are the axial one? The axial ones, that will be the shown over here in the red color. We can say that the vertical one, vertical bonds, actually that are the parallel to axis of symmetry. Where the atoms or the hydrogen atoms which are shown in a blue color, that are directed at the angle of 109 degree 28 minutes. So that are directed at the angle of 109 degree, they are pointed outwards. So ultimately these bonds are called as equatorial bonds. Then that's each carbon atom in the chair form will be attached to one axial and one equatorial. So if you consider, uh, out of these six carbon, each and every atom is attached to one equatorial and one axial. The equatorial axial. So every atom, every carbon atom is attached to one axial and one equatorial. The red hydrogen are called as axial, and the blue one will be considered as a equatorial one. So these are the two sets. So if we count that, then ultimately there are six equatorial and six axial hydrogens will be there. Then the another conformations that is present over there, that is the boat conformation. So in boat conformation, there are four boat axial bonds, four boat equatorial bonds. So you can clearly see here the bonds, the hydrogen bonds, or the carbon hydrogen bonds between this red hydrogen and the carbon, that are called as a axial. It is not exactly axial, that's why it is called as a boat axial. Similarly, the hydrogen which are shown over here, that are equatorial bonds, they are representing equatorial bonds. Then the remaining two which are shown over here, that are shown in a different color. So the green hydrogen and pink hydrogen, the green hydrogens are called, considered as a flagpole bonds, whereas the the bonds which are pointed outwards of this boat, you can clearly see here why it is called as a boat conformation, because the shape of this conformation is like boat. So that's why it is called as a boat conformation. And these two hydrogen which are pointing out will be considered as a bowsprit bond, whereas the hydrogen which are pointing inwards inside the boat, ultimately they are called as a flagpole bonds. So in order to understand this structure, we have to understand three-dimensional arrangement of this cyclohexane ring. So I will show you video, so that will give you clear idea about this. So see, let's see this video. So the play, if you see this cyclohexane ring, so from the top side, ultimately it will looks like planar only. But if I rotate this ring, then ultimately you will get clear idea what is the actual arrangement of this cyclohexane ring. So see here, here we can clearly see the it is chair like, it has chair like three-dimensional shape. And then to each atom, each carbon atoms which are shown over here, two hydrogen atoms are attached, and each atom, each hydrogen atoms having a particular orientation. It may be either vertical or it is pointing outward. So the bonds which are vertical will be considered as axial in a simple word, or the bonds which are parallel to center of axis, a symmetry of axis, symmetry axis, will be considered as a axial bonds. And then the points, so which is shown over here, you can clearly see here the bonds I'm highlighting, that are considered as a axial one. Three are at the top side, and three are at the bottom side. So total there will be six axial Three will be on a top side, three will be on a bottom side. So if I rotate this molecule, then we will get a clear idea about the presentation of this molecule. So there are total six axial atoms. Three will be on the top side and three will be on the bottom side. If I keep molecule like this, then we will try to understand which are the equatorial one. The equatorial one, which are pointed at the which are directed at the angle of 109 degree 28 minutes. So I'm highlighting this. See here. So this bond, this bond, this particular bond, which are pointing outwards, will be considered as a equatorial. Remaining two are this one. So there are total six bonds, carbon hydrogen bonds. They are pointing outwards. If I rotate this molecule, then you will clearly get idea what I'm saying. Okay, so overall there are six such atoms. They are pointing outwards and they will be considered as a equatorial one. So then if you consider the boat conformation, then if we consider a boat conformation, then we know in a boat conformation the different type of arrangement than the chair conformation is observed. So let's see a three-dimensional structure of boat conformation. So from the top side view, it will appear as planar only. But now see, now this is the three-dimensional structure. Three-dimensional structure. Now we will rotate this molecule. If I rotate this molecule, then ultimately from the side view, you can clearly see somewhat. It is not exactly boat, but you can clearly see a boat-like shape over here. So boat-like shape will be like this. This is the boat-like shape over here. If I highlight that point, carbon atom, so which is present at 1,4 position, then you will get clear idea. Okay, this is the boat shape over here. Then again, these bonds are divided into four different types: boat equatorial, boat axial, and then flagpole bonds and bowsprit bonds. So we will try to understand that by highlighting this. So now I'm highlighting these equatorial bond, axial bonds, both axial bonds. So this one is axial one. This one is also axial. There are total four axial. Four will be on front side and two will be on front side. Two will be on back side. Okay, these are the highlighted one. Four are both axial. That is not exactly axial. Then when you talk about the equatorial one, so again there are four equatorial. I'm rotating this molecule so you will get clear idea. Then we will try to understand the bowsprit and flagpole positions. So if I mark this 1 and 4 position of this boat, so this is the boat shape, puckered shape, okay, boat shape. Uh, then inside of your boat, then if I label this 1 4 position, then what are the atoms attached to these carbon atoms? They are not considered as equatorial or axial, but another notations are given over here. This is the atoms which are attached over here, or they are pointing inside, will be considered as a flagpole. So this atom and this atom, and these are the flagpole atoms or flagpole bonds. Similarly, the other two atoms that are attached over here, that will be considered as a bowsprit atoms. So these are the bowsprit atoms. So I hope you have understood this structure.